Hello guys, welcome back to another video on my channel. I would also like to do another integral in this video. So let me write the question down. So I is integral from 0 to 1 of x to the s minus 1 over 1 plus x dx. Now this isn't the worst integral we've done in a long time, but I think it's sort of an important result that we're gonna use for an upcoming epic video. So first thing to notice is the bounds of integration 0 to 1 and the structure of the denominator. We could probably rewrite it as x to the s minus 1 over 1 minus x dx. Now the reason for doing that is the formula of the geometric series. Say a over 1 minus r was just the infinite sum n equals 0 to infinity of ar to the n. So I really want to use this formula, and this is of course only valid when r is less than 1. That's the condition for the region of convergence of this infinite geometric series. In our case, we have absolute value minus x to be less than 1, which will also always be true in this interval of 0 to 1 that we're concerned to work with. So that's just a tiny side note. So let's expand it in terms of an infinite series. So we have sum from n equals 0 to infinity of this top term is as it is minus x to the n dx. We can interchange the infinite sum and the integral for uniform convergence reasons. So we have this, maybe minus 1 to the n can come outside like that. Let me write this more succinctly. We have a collective x to the n plus s minus 1 dx, which we can integrate really nicely. It's just a simple polynomial. It's going to be x to the n plus s divided by n plus s evaluated at 0 and 1. Well, the 0 value of this polynomial is always going to be 0. So we just have this over n plus s. Well, how do we evaluate this infinite sum? Well, let's write some terms down for this infinite sum. Let me use a different color here. Let's use red. Tribute to black pen, red pen right here. But also the color of the logo of my channel. The 0 term is going to be 1 over s. The first term is going to be s plus 1. So you get the idea, and so on. Now what I want to do is I want to separate the even and odd terms. So I can restructure this sum to say run from n equals 0 to infinity. Now the even terms, if you look at them, the just the positive terms, they look like 2n plus s, right? Because we're starting with a 0, so that n equals 0 works, and when n equals 1, this is s plus 2, so we get this term. That's fine. So we're going to generate all of these even terms. Now for the odd terms, I'm going to write them minus, because they're always followed by a minus sign. And the odd terms are going to happen for, say, 1, n equals, well, we want whatever's added with s to be 1 when n equals 0, so that we get s plus 1. One way of doing that is n plus 1 plus s. So if you plug in n equals 0, we have s plus 1. N equals 1 with s plus 3, so we're going to get the next negative term, and then the pattern follows. So this is really what our integral has come down to. The fate of the integral is in the hands of this infinite sum. Now I would like to just free the coefficient of the index here. I'm going to pull the 2 out from the denominator, giving me a 1/2 1 over n plus s over 2 minus 1 over n plus s plus 1 over 2. Now this might seem a little reminiscent. Let me just remind you what we can do here, the great things we can do. Digamma of z, or let me just say s for more clarity, minus Euler-Mascheroni constant plus sum from n equals 0 to infinity of 1 over n plus 1 minus 1 over n plus s. Now let's see what we have here. We have this term, which would correspond to this term here. And then this term would correspond to another one of these. So what we need to do is add this common factor, subtract this common factor, 1 over n plus 1, in both of those, and then hopefully also an Euler-Mascheroni up front, and then we can probably generate the difference of two digamma functions like this. So maybe I'll try adding it. 1 over n plus 1 minus 1 over n plus s plus 1 over 2. Now I have to subtract that 1 over n plus 1. Maybe I can, and then add that term s over 2. Okay, that's fair. If you want, and if it's not clear, maybe I can like add and subtract Euler-Mascheroni constants as well. But you can see there's a difference of digammas here, and the Euler-Mascheroni constant is the only thing that's common in their expansion. So it really doesn't matter even if I like write it down explicitly out there. But you can clearly see this is finally going to evaluate to 1/2 digamma of, let's see, s plus 1 over 2. Just plugging it into this definition in white, minus the digamma of s over 2. Now what can we do? Can we simplify this further? The answer is yes, and this is for only those who've worked with some identities of the digamma function. What we can do is we can work with the duplication formula for the digamma function. So digamma of 2s is 1/2 digamma of s, 1/2 digamma of s plus 1/2 plus natural log of 2. Now in our case, we can sub, instead of s, we can sub in s over 2, so that we have s here, s over 2. So double angle has become a half angle formula, half argument formula more than angle, plus natural log of 2. We can see that digamma of s minus the digamma of s over 2 from this formula are just going to be 1/2 digamma of s plus 1 over 2 minus a 1 and half, or minus 1.5 will give you a minus half digamma of s over 2 plus natural log of 2. So to get the blue part, I just need to subtract the natural log of 2 from both sides. and we get what we wanted here. And now it's just time to plug everything back in the grand finale. So I is going to be digamma of s minus digamma of s over 2 minus the natural log of 2. And there we go. That's the solution to our integral. Integral from 0 to 1, x to the s minus 1 over 1 plus x dx. I'm going to use this result a lot in the next video, so please stay tuned. If you don't know how I got this formula of the digamma, watch the previous videos. I've made a detailed derivation of that, of this X series representation of the digamma, and also the duplication formula of the digamma. So please watch those videos. It's probably in the card there somewhere. And in the meantime, stay home, stay safe, keep doing math, and peace out.